So in this example problem, we're given an arc segment that is defined by this equation, and we're asked to determine what is the centroid of this rod that's given below. We're given that the rod, what we're trying to find here is our goal is we want to find the location of our centroid. So where is I want to determine what is x bar and what is y bar for this rod. Right. So in order to complete this, to determine x bar and y bar, we need to do a couple things. The first thing we're going to do is we're going to define our differential element. All right. So on the diagram, it's already been drawn a little bit, but I'm going to blow it up here. All right, so we have our differential element dl, all right, and then the centroid of our differential element, so just the element itself, this is our x tilde and y tilde terms. Those are just going to be equal to the coordinates along our parabola. So that should be equal to x and y. Right, so x tilde would be equal to just x, and y would just be equal to the y coordinate at that point. Right. So after we have our formula, or after we define our differential element, the second thing we need to do is we need to identify the formulas that we need to determine x bar and y bar. Right? So if we looked back in our packet or in the book, we would have defined for a line element, we would have x bar would be equal to x tilde, the integral of x tilde dl divided by dl, the integral of dl. Alright, and then we have y bar we define as being equal to y tilde dl over the integral of dl. Alright, so the only thing left that we must define here is we need to define dl. So dl could be equal to the integral of 1 plus dx over dy squared dy, and then or it can be equal to, dl can be equal to the integral of 1 plus dy squared dy over dx squared dx. Alright. So in our case, our relationship is going to be we have x is equal to y squared. So if we took the derivative of y of x with respect to y, that's going to be a lot easier of an integral to evaluate. So we're going to want to keep everything in terms of our dy equation here. All right. So we end up using this one. All right, but just because it's easier in this situation. All right. So we're going to now solve our integrals. Alright, so if we solve our integrals, we would get x bar is going to be equal to we're going to have x tilde, we're going to substitute in here. So x tilde we have is just equal to x, so you can say that this would be equal to x here, and then our dl term we're going to use the square root of 1 plus dx with respect to dy. So if we took the derivative of both sides here, we would end up getting dx over dy would be equal to 2y here squared dy. Since the dl term is in terms of y, we should put x in terms as y as well. So we're going to subtract that x, and we're going to write y squared here. Alright. And the only thing left is the bounds of our integral. So the bounds of our integral will go from the leftmost bound, or I should say the bottom bound in y, to the upper bound in y. So for this parabola, we go from y is equal to 0 to y is equal to 1 meter. So the bounds of our integral will be from 0 meters to 1 meter here. Alright. And then on the bottom of our equation, we would just have just the integral of dl. So it would also go from 0 to 1 meter, and it would just be this term. It wouldn't be the x tilde term, so it would just be equal to the square root of 1 plus 2 of y squared dy. Okay. So what we needed, these integrals are a little bit tricky to integrate. They're just not simple like square or cubic functions, polynomial functions. So what we need to do is we need to go back in our packet and look at our table of integrals. All right. So if we look back at our table of integrals, we'll notice that there's a couple of cases that would really help us solve our problem. So for our numerator, you could use this case here. And then for our denominator, we could use this formula here. Alright, so in our case, we need to write our integrals in terms of this form here and this form here. So let's do that, and then we can evaluate our integrals. Alright, so in order to do that, we have to rewrite our equations like this. So we're going to bring out a number 2. If we do that, we would end up with this equation here. On the top. And then we'd also bring out a 2 on the denominator, and we'd end up with 1/2 squared plus y squared dy. Alright, so the 2's will cancel each other out, and then in this case we have our a, or our constant, is going to be equal to 1/2. So if we plug that in, and then the bounds of our integral are 1 meter and 0 meters, so we could plug in, so if we plug in this information, we're going to go back to our table. Alright, so we have a is equal to 1/2, and then x goes from 0 meters to 1 meter. So if we plug all that in, we would get so we would get 1/2. So if you plug all this information into these equations, you could solve for the value of this integral here. All right, you did the same thing on the top. You would just plug in a is equal to 1/2, and then you would evaluate x as equal to 1 meter. Then you would evaluate x at 0 meters, and you would subtract the difference between those two to get your answer. If you did all that, what you'd end up getting is the top integral. You'd end up getting 0.6063 meters cubed over the denominator, which would be equal to 1.479 meters squared, and then you'd end up with a centroid of 0.410 meters. All right, and then we could repeat the same process for the integral for y bar. So for y bar, the only difference is instead of having y squared multiplied by dl, we just have y, and then we have the same integrals here. And the denominator integral would be the same as above that we used for x squared. Alright, so we can rearrange it in terms of integrals we can solve using our integration table. Alright. Alright, so we're just putting it in form that we can solve using our integration table. Alright, and once we have both our numerator and denominator in forms we can solve with our integration table, if we evaluated those two integrals, we would have gotten 0.8484 meters cubed divided by 1.479 meters squared, which would be equal to 0.574 meters. Alright, so we now have our two answers, x bar and y bar, for our integrals. Please notice that the denominator on both of these integrals is the same. So don't do that same integral twice. So you should only have to do 3 integrals for a line equation. One for x, the numerator for x bar, the numerator for y bar, and then the denominator for them both is shared. All right. So just to summarize what we did, we first defined our differential element. All right. Once we identify our differential element, dl, and x tilde and y tilde, we then identified the formulas that we needed to use. So we determined our formula for x bar and y bar that was given to us in the lecture packet or in chapter 9 of the book. Once we had that, we had to define which definition of DL we would use. So we picked the differential element that would be easier to differentiate, so the dx dy term or the dy dx term. So we thought that the dx dy would be a much simpler integral, so that's why we picked that. Once we have those all defined, we would then just plug in our values for x bar. We would just plug in the values into our two equations, and we would just solve the integrals. So it's pretty simple. Once you have your elements defined, you just have to do the math. Okay? All right, and that concludes this example on how to calculate a line integral using the definition of a centroid.